Okay, so welcome back everyone. Sorry for the slightly late start. We were setting up some new technology, wireless microphones. So what are we covering this week? Well, last week we finished talking about sorting algorithms, right? And why did we cover sorting algorithms? Well, if you have a sorted array, then you can search much more efficiently, right? You can search in O log n time. Right, so this week we're going to talk a little bit about ADTs first, which are a really important concept, and then we'll start talking about binary search trees. Okay, so abstract data types. So what are they? Okay, so yeah, before we actually get to abstract data types, what is abstraction? Right, so abstraction is a really important concept, right? So if you go on the internet and you do a search, you'll get lots of different, definitions, lots of explanations for what abstraction is. Right? But here's a definition which I'm a bit satisfied with. So abstraction is the process of hiding or generalizing the details of an object or system just lowering the volume a little bit. Okay, so abstraction is the process of hiding or generalizing the details of an object or system to instead focus on its high-level meaning or behavior. All right, and we'll see what that actually means. So what are some examples of abstraction? Right, so one is using an int or double in C, right? So when, you probably know that an int is just a collection of bytes, right? And each of those bytes is a group of 8 bits, right? So ints and doubles are all just zeros and ones behind the scenes. And when we use ints and doubles in our program, we don't really need to care, most of the time, we don't need to care about the fact that these are just series of bits and bytes, right? Because we just use them to add together numbers, to subtract, to increment, and so on, right? So usually we don't rely on the fact that these ints and doubles are just series of bits and bytes, right? So we're sort of hiding the detail of what ints and doubles actually are, and we are focusing on their high-level meaning, right? So ints and doubles are numbers, right? Ints are whole numbers, doubles are, real numbers. Another example is writing a function, right? So when you have, a long piece of code and, your tutor looks at it and says, this function's a little bit long, you should probably break that up into functions, right? What they mean is that you should, move some part of your code that performs some logical step into a separate function, right? And what's the benefit of creating a function? Well, not only do you get shorter functions, which improves the readability, usability of your code, but also you give that function a name, right? A descriptive, meaningful name that describes what the function does, right? And so we've sort of taken that bit of code, and we've sort of hidden that into a function, and now we have, because we've given the function a name, we've given that piece of code a high-level meaning, right? Or another example in programming is writing a program in C instead of assembly, right? So you might know that, when you write a program in C and then you compile it, it gets compiled down to assembly, right? So you could if you wanted, you could write your entire program in assembly, right? But you probably wouldn't want to do that because assembly code is really difficult to read, really difficult to understand, right? So when we write a program in C, we're sort of hiding that level of detail, which is that C gets compiled down to assembly code, right? And instead, we can write much more complex programs more easily in C. Right, so another example which doesn't even involve any programming, but still related to computer science, is to model the states of a system by using a state machine. So if you've done COMP2521, right, that course will talk about finite state machines, right? And what these are is you're basically just enumerating the states of the system, right, and the transitions between the states, right? And this is a model of a program which in reality would be implemented, in a programming language, right? So here's an example of a state machine for a turnstile. So turnstile has two states. It could be locked, it could be unlocked, and when you put in a coin, it becomes unlocked, right? So after you put in the coin, you can walk through it, right? So, yeah. So here's some real life examples of abstraction. So one, when we drive a car, right? So you know that when you drive a car, you use a steering wheel and pedals, right? And also a gear stick and a few other components, right? But you don't care about what's happening behind the scenes, right? In the engine, for example. So we've sort of hidden that detail away, and instead we're just using these, higher-level components to operate our car. Right, another example is a television, right? So a lot more people don't have TVs nowadays, but when you operate a TV, you use a remote control, right, or an on-screen display, and then you use the buttons to operate the television, right? So you don't open up the television and mess around with its innards, right? You just use the remote control. Right, another example is when you're withdrawing and depositing money, right, from your bank account, right, you use an ATM. Right, so, how does the bank account actually work behind the scenes? Who knows? There's probably some complex system involving a database, involving some, security systems. But in your perspective, it doesn't matter because all of that detail is hidden behind the scenes, and you just interact with an ATM. Right? Okay, so why do we use abstraction? Well, in order to use a system, right, we shouldn't need to know the lower level details of how it works, right? All that should be enough is to understand what its components do, and we shouldn't need to know how those components work, right? Because we shouldn't need to. All right, so that's abstraction, and now we'll talk about what abstract data types are. Right, so first of all, what is a data type? Well, a data type is a collection or grouping of values, right? And I say collection because you might have a data type that's just a single value, like an int or a double, right? Or you could have a data type that's composed of a bunch of smaller values, right? So you could have arrays, which are a contiguous sequence of items of the same type. Right? You could have structs, which contain fields of different types. Right? So all of these are data types, and along with those data types, we have operations, right, that we use on those values. So for example, for ints, we have addition, multiplication, comparison with less than or greater than, and we also have arrays. So arrays, you can use index lookup, you can index into an array, you can set an index of the array to a particular value, and so on. Right, so what is an abstract data type then? Well, an abstract data type is a data type which is described by its high-level operations rather than how it is implemented. Right, and we'll see lots of examples of that throughout the lecture. Right, and so data type that's described by its high-level operations, and these operations, so the set of operations provided by an ADT is called its interface. Okay, so for example, if we go back to one of the real-life examples, so when we drive a car, the interface to the car would be the steering wheel, the pedals, the gear stick, and a few other components. Right? The interface to the television would be the remote control, right? Because that's how you operate the TV. And the interface to your bank account is the ATM, right? Because it allows you to perform these operations such as deposit, withdraw, and check your balance. All right, so what are some other features of ADTs? So for an ADT, the interface, which is the set of operations provided by the ADT, is separated from the implementation, right? So think back to the example with the car, right? The interface, which is the steering wheel, the pedals, and so on, that's separated from the other components of the car, right? So the engine and so on, because you don't need to worry about how that stuff works. Right? Okay, so users of the ADT only see and interact with the interface, and builders of the ADT provide an implementation. Right, so as a user, you only interact with the operations provided by the ADT. Right? Meanwhile, the people who are actually responsible for building the ADT, they provide the implementation. For example, like a car manufacturer. Right? Right, so what are the benefits of ADTs? So first of all, they facilitate decomposition. So what does that mean? That means it allows us to produce shorter, more understandable, more readable, more maintainable pieces of code, right? Pieces of software. Right, so let's just split our code into maintainable, organized pieces. Right, and another benefit of ADTs is that because the interface is separated from the implementation and users only interact with the interface, we can make changes to the implementation without affecting users. Right, so think about the example with the ATM. Right, so it doesn't matter what's going on behind the scenes in the bank systems. If they make changes, it doesn't affect you, right? Because all you're doing is interacting with the ATM. Right, and yeah, it improves readability and structuring of software, just like I said earlier. All right, so interfaces and implementations. So what do interfaces provide, right? So an interface is the set of operations provided by the ADT, right? So an interface provides an opaque view of a data structure, right? So opaque meaning you can't see through it, right? So you can only see the interface, right? You can't see through to how the ADT is implemented. Right, function signatures for all operations. So in the code, when a user uses an ADT, they'll be given all the functions that they can use, right? Each function corresponds to an operation that they can perform on the ADT. Right, and the semantics of the operation. So what does semantics mean? It means meaning. So the meanings of all the operations. And since the user of the ADT can't see the implementation, it's really important that the documentation is detailed enough that the user knows how to use the ADT, right? Because if the documentation isn't clear enough, then users could get confused as to what the ADT is actually doing, right? So clear documentation is really important, right? So what would we include in documentation? We would include, what are the inputs of the operation? What are the outputs of the operation? What are the requirements for you to actually use the operation? Right? Because maybe sometimes the operation cannot be used, right, with specific inputs. Okay, and an interface basically gives you a contract between the ADT and the clients, right? And we'll get into what that means in a bit. All right, and then implementations, what do they provide? Well, they provide a concrete definition of the data structure, right? Because an interface doesn't provide that. The interface only provides the operations that you can perform on it, right? The implementation actually defines the data structure, right? And it also provides implementations for all the operations. Right, so now getting into more detail. So when we are writing code implementing an ADT or defining an ADT, right, so what files do they go into, and what do those files contain? Right, so because the interface and implementation are separate, right, they go into separate files. Right, so the interface of the ADT is defined in a .h file, and it provides an opaque view of a data structure, but how is that view actually provided? Well, we have a type def in the .h file, which looks like this. So type def struct t star capital T. Right, so the t's will be replaced with the name of the actual ADT. But remember what type def means. So type def means type def lets us give a type a new name. So what this type def actually means is it's giving a new name for struct t star, right? So pointer to a struct. Right, so it's saying that instead of saying struct t star, we can just write t instead. Right? And that sort of hides the fact that a t is actually a pointer to a struct, right? Because users don't need to know about that. All right, and in the interface, we don't provide a concrete struct definition, right? So that will be provided in the implementation. All right, so the interface also contains function signatures, right? And that would be provided via function prototypes. Right, so the prototypes will have all the types of all the inputs and the types of all the outputs. Right? And in order to describe what they do, we have documentation, which is provided via comments. Okay, and yeah, so an interface basically forms a contract between the ADT and its clients. Right, so what does that mean? So the documentation describes how each operation should be used. Right, so for example, one comments for an operation might say the integer that you provide has to be positive. Right. So when the documentation says that, well, the user should make sure that whenever they use that operation, they pass in a positive number, right? Because if they pass in a negative number, then that's not expected by the implementation. Right. All right, and yeah, the documentation also describes what the expected result is, as long as the operation is used correctly. Right, so we'll get into an example in a bit, don't worry. So now for the implementation. So the implementation of an ADT is defined in a .c file. Right, so what does it provide? Provides a concrete definition of the data structures, so the definition of the struct, and also implementations for all the functions. Right, and here's one last bit about conventions in this course. So in this course, when we define an ADT, we'll define them in names starting with an uppercase letter. Right, so for example, for a stack ADT, the interface will be defined in stack.h, and the implementation will be defined in stack.c. Right, and function names are, they use this naming style, Pascal case. So they, it's like camel case, except the first letter is capital. Okay. And the function names begin with the name of the ADT. All right, so in order to create and use an ADT, what operations, so what do we do? Well, first of all, we need to decide what operations we want to provide. Right, so often these operations will involve creating an instance of the ADT, querying the ADT, asking questions about the data, and manipulating the data. Right, so for example, inserting, deleting. Right, and we also need to decide on what their inputs and outputs are. Right, for example, if you want to, if your ADT is like a collection of items, then one question you might ask is, what is the size of the collection? Okay, and what are the conditions under which the operations can be used, right? And we'll get into an example of that. Okay, so after you've decided what operations you want to provide, you need to provide the function signatures, right? And the documentation for all these operations in the .h file. And after you've done that, the developer of the ADT actually implements the ADT in a .c file, and the user of the ADT, what they do is they just hash include the .h file in their program and use the provided functions. Right, so here's an example of an ADT, a really simple example. Right, so a bank account. Right, so a very simple bank account. What operations can we perform on a bank account? Well, first of all, we can open an account. Right, we should be able to open an account. We should be able to check the balance in our account. Right, we should be able to deposit money, and we should also be able to withdraw money. Right, these are all these simple operations that we need. Right, so here's what an interface might look like. Right, so first of all, we have that type def that I said earlier. So we say type def struct account star account. Right, that means account with a capital A, that's the same thing as saying struct account star, right? And when a user uses the ADT, they just use this name, account, right, with the capital A. Right, and here are all the operations that we want to provide. Right, so the first one is to open an account. That's pretty simple. Right, it doesn't take in any inputs, but it returns a new account. We also have close an account just for completeness. We have an operation to get the balance of the account, right? So the function takes in an account and it returns an int, right? Which is how much money is in the account. Right, we have account withdraw, which withdraws money from the account. Right, so that function takes in an account and also an amount. Right, so for example, I want to withdraw $20. Right, now this function returns a bool, right, and this is a design decision. Right, so the thing is, when you withdraw money, right, and you specify how much you want to withdraw, your account might not have enough money, right? The balance might not be high enough. So in this case, if the account has enough balance, then the function will return true, right? Otherwise it will return false. Okay? And this function also makes an assumption, right? So it assumes that the amount is positive, right? Because it doesn't make sense to withdraw a negative amount of money or a zero amount of money, right? So the function assumes that the given amount is positive, and if it's not positive, then it could just print an error message. Yeah, question. Yeah, so in order to add money to account, you would use deposit. Yeah. Yeah, you would error check for that. Yeah. But yeah, since this is the purpose of this is to like simulate an ATM, you shouldn't really there's no real way to withdraw a negative amount of money. Okay, and there's finally an operation called deposit, which lets you deposit money into the account, right? And it assumes that the given amount is positive. Right, so here is one possible program which uses the account. All right, so first of all, we create an account. Right, so we open an account, then we print out the balance. Right, so when you open an account, the balance is going to be 0 at first. Right, so we print out the balance and we expect the balance to be 0. Right, now we call account deposit and we deposit $50. Right, so what is the result of that? Well, when we check our balance after we deposit, it should have gone up by 50. Right, that's That's our understanding of how a bank account works. Right? When you deposit money, your account balance should go up. Right? Now, we withdraw some money, so we withdraw 20, and our understanding of that is the balance should go down by 20, right? So after we print out the balance, it should be 30. And then we can also try and withdraw an amount that we don't have. Right? So if we withdraw 40 now, well, we only have $30 in our account. Right? So we can't withdraw that amount. And once we print out the balance, it should still be 30, right? Because 40 is an invalid amount. All right, then we just close the account. So, there might be some problems with this because when you close the account, there's still money in the account, but let's not worry about that. All right, so I have an example of the program here. All right, so my file goodcustomer.c does pretty much what's on the slide. Right, so the hash includes account.h. Right, account.h, let's open that first. So that contains all the operations and documentation for each operation. Right, so it specifies what are the inputs, what are the outputs, and any constraints on the inputs. Right, so this is basically what I showed before. Now, good customer, so it opens an account, deposits $50, withdraws $20. I've also added a few checks here to check the return value of withdrawal and print out a message if it returns false. Because if it returns false, that means there wasn't enough balance. Right, so let's try and compile this program and run it. Whoops. So all right, let's compile the program again. Good customer. And we can see that it prints out prints out 0 at first. Then it prints out 50. Then it prints out 30. Then it prints out withdrawal failed, right? Because you can't withdraw $40 if your balance is 30. Right? Then your balance is 30. All right, so that's how you interact with an ADT, right? You use the functions in the .h file, right? And notice that I haven't shown you guys the implementation, right? That's because the user of the ADT doesn't need to know about the implementation. All they use is the interface, right? And they use the documentation in the interface to reason about their program, right? Okay, so now I'm going to show you what you can't do with an ADT. Right, so this is called breaking abstraction, and what the program is doing is it's trying to access a field of the struct directly. Right, so we create, an account using account open, then we try to access the struct and set the balance field to 1,000,000, right? And in the real world, the equivalent of this would be to hack into whatever database that the bank uses and setting your balance to $1 million, right? Wouldn't that be nice? So yeah, so when we print the balance, then if this works, then we would expect for it to print out 1,000,000, right? Then we close the account. But what happens when we try to compile this program? So here's the program in badcustomer.c. When we compile this program, make bad customer, it gives us a compile error, right? The compile error is incomplete definition of type struct account, right? So what does this mean? Well, it means that the struct accounts, so the account struct isn't defined, right? And why isn't it defined? Well, when we compile programs, right, when we compile programs involving multiple files, each program or each file is compiled separately, right? So in this case, the program consists of badcustomer.c and account.c. Right, now, each of those files is compiled separately. So when we compile badcustomer.c, let's check what badcustomer.c actually contains. Right, so badcustomer.c contains a hash include for account.h. Right, so let's see what's in account.h. Right, so account.h contains this mysterious typedef. Right, so typedef struct account start account, and it contains all of these function prototypes. Right, but it doesn't contain the definition of the account struct. Right, so the badcustomer.c program has no knowledge of what the account struct contains. Right? So when we compile the program, this gives us an error because the compiler doesn't know what's in the account struct, right? And therefore, it doesn't know, whether this operation would be valid or not. Okay. So that's why the compile error happens, right? So incomplete definition because we haven't defined struct account. Okay, and if we now have a look at account.c, right, so here's the implementation, and we notice that the field isn't even called balance, right? It's called bal, right? So if you think, well, what if I try to set the bal field to 1 million instead of balance? Will this work? Well, let's see. Right, so now we're trying to set the bal field to 1 million because we know that the struct contains a field called bal. Well, when we try to compile this, it still doesn't work, right? That's because when we compile badcustomer.c, right, that program, that file, doesn't include the definition of the struct, right? So the program still doesn't compile. Okay. So when we actually compile the program, each file is compiled separately, right? So account.c is compiled, then badcustomer.c is compiled, and then finally they're linked together. Right, so the error happens when we're compiling badcustomer.c. Okay, so here are some more examples of ADTs. So we have stacks, queues, sets, multi-sets, map, graphs, and priority queues. We'll talk about stacks and queues now, and then some of these we'll talk about later in the course. So graphs and priority queues we will definitely cover later. All right, so let's talk about stacks and queues. So stacks and queues are really common data structures in computing. They're part of many important algorithms, and they are good demonstrations of the benefits of using an ADT. Okay, so first we'll look at what a stack is. All right, so a stack is a collection of items. So it's a linear collection of items such that the last item to enter is the first item to leave. Right, so it's called a last in, first out data structure, and you can think of it as a stack of books, right, or a stack of plates. Right, so if you have a stack of plates, right, and you want to add a plate or remove a plate, you can only add it to the top, right, and remove from the top. Right. So you can think of it as a literal stack. All right, and where are stacks useful? Well, they could be useful in implementing web browser history. Right, so for web browser history, what a browser could do is whenever you click on a new link, right, that link gets added to the stack, right? You click another link, that link is added to the stack, and when you go back, you remove the link at the top of the stack, and you go to whatever page is at the top, right? So that is one application of stacks. Text editor undo redo is another application. Right, so whenever you perform an operation in a text editor, you push that operation onto the stack, and if you make a mistake and you have to undo, then you remove that operation in the stack, right? And then you undo whatever that operation was. All right, balanced bracket checking. So we'll actually have a look at that. And here are some other applications. So HTML tag matching, similar to bracket checking. RPN calculators, you can look up what that means. Even function calls use a stack, right? And yeah, don't get confused between this kind of stack and the stack in your program memory. So these are two completely different things, right? So a stack, it's a region of memory in your program, but a stack is also an ADT. So yeah, just don't get confused between the two. All right, so what are the operations, right? So a stack is an ADT. What are the operations that we want to provide? Right, so the two main operations that we want to provide are push and pop, right? So push adds an item to the top of the stack, pop removes an item from the stack, right? Simple enough. And what are some other operations that we want to provide? Well, maybe we want to provide a size operation, right, that returns how many items are on the stack, right? Because that might be useful for maybe checking if the stack is empty. Right? Another operation is peek. So, sometimes you want to look at what's on the top of the stack, but not remove it, right? So in those situations, peek is a useful operation. And of course, we want to be able to create and free our stacks. Right? So constructor and a destructor. All right, so here's how we might use a stack, right? And I'm not showing you any code yet because remember, with an ADT, right? With an ADT, we are concerned with the operations provided, right? In order to use it, we only care about the operations provided, right? So we don't need to know how the stack is implemented in order to be able to use it. So I'm showing you a use case of stacks now, and then we'll get on to the implementation later. Right, so a stack, so one application of a stack is to check for balanced brackets. Right, so here's an example of balanced brackets. Right, so you've got the normal bracket, then you've got the square bracket, then you've got the curly bracket. So these are opening brackets. Then you've got the closing curly bracket, then the closing square bracket, then the closing normal bracket. Right, and here are some examples of unbalanced brackets. Right, so in the first example, we have a pair of matching brackets. Right, so we've got an opening bracket and a closing bracket, but then we've got a few extra closing brackets, right? And this is unbalanced because there's no opening bracket earlier to match them with, right? So even though the number of opening and closing brackets is the same, this is unbalanced. Right, in the second example, we've got an opening normal bracket, square bracket, and curly bracket. Then we've got a closing curly bracket, which matches with this opening curly bracket. But then we've got a closing normal bracket, right, which doesn't match up with the square bracket here. Right, so this is unbalanced. Here's another example. So we've got a opening normal bracket and square bracket, and then closing square bracket and normal bracket. So these four brackets match up. But then we've got a bunch of opening brackets, and that's it, right? We haven't got any closing brackets to match them with. So this is unbalanced as well. Right, so here is, so what is the process? How do we check if this series of brackets is balanced or not? Well, the idea is whenever we see an opening bracket, we push it onto the stack, right? And then whenever we see a closing bracket, right, we check to see if it matches the bracket at the top of the stack, right? And then there are a few edge cases that we also have to handle, but that's the main process. Right, so I'm going to show you one example where the brackets do match. So this is just the example from earlier. Right, so when we see an opening bracket, we push it onto the stack. Then we see an opening square bracket, so we push that onto the stack. Then we see an opening curly bracket, so we push that onto the stack. And now we see a closing curly bracket, right? So we look at the bracket that's on top of the stack, which is an opening curly bracket, and these two brackets match, right? So that check succeeds. Then we see a closing square bracket, so we check what bracket is on top of the stack, which is an opening square bracket, and these brackets match, so we're fine. And then we see a closing normal bracket, right, which is going to match the bracket on the top of the stack. Right, so, and finally, we reach the end of our input, and the stack is empty. So we're good. Right, so in this case, the brackets are balanced. Right, here's an example of where the brackets aren't balanced. So, okay, not sure why the 2 is there, but just ignore that. So we have the normal opening bracket, right? So we push that into the stack. Then we see a opening square bracket, so we push that into the stack. Then we see a opening curly bracket, we push that into the stack. Right, then we see a curly bracket, closing curly bracket, and that matches. Right, so we remove this bracket from the stack. Then we see a closing normal bracket, right, and this doesn't match the bracket that's on top of the stack. Right, so it doesn't match, so our check fails. Right, so the brackets aren't balanced. All right, so here is the interface to the stack. Right, so we have stack new, so that creates a new stack. We have stack free, which frees a stack. We have stack push, which pushes an item onto the stack. But we have stack pop, so these operations I mentioned earlier, all of them. Right, and an important thing to note here is that when we pop from the stack, right, the stack can't be empty. Right? It doesn't make sense to pop from an empty stack. Right? So there's that. Then there's also an operation to get the size of a stack, and there's also a peek operation to get the item at the top of the stack. Right? The peek operation also has the requirement that the stack isn't empty, right? Because it doesn't make sense to check what's at the top of the stack if it's empty. All right. So now I'm going to implement this bracket balancing program using this interface, right? So when we use a stack, remember, we don't need to worry about how the stack is implemented, right? So let's go to stacks, right? And first I'll show you what's in stack.h. So in stack.h, we have the exact same contents as I showed you earlier. Right, so all these operations, and if you're wondering what item is, because item is not a normal type in C, it's a type-def int. Right? And the reason we use this is because it makes it really easy to switch out types. Right? So if you want to switch from an int to a double, for example, you can just change the type-def here, and then your stack will take in doubles. All right, so what I'm going to do now is implement the bracket balancing. Right, so at the beginning of the program, we want to create a stack. Right, so stack s equals stack new. Right, so we create a stack. Right, and now we want to read in inputs. Right, so the way I'm going to do that is I'm going to create a variable for a character, and then use getChar. Right, so while ch equals getChar is not equal to EOF. Right, so what I'm doing in the while loop condition is I'm reading in a character into ch, and then I'm checking if it's not end of file. Okay, so now the important characters for us are opening brackets and closing brackets. Right, so these are the only characters of interest. If there are any other characters, we just ignore them. Right, so first, let's check if the character is an opening bracket. Right, so if ch is one of these, so if ch is an opening parenthesis, or an opening square bracket, or an opening curly bracket, right, then what do we want to do? All we want to do is to push it onto the stack, right? So we call stack push, right, and we give it the bracket, right? So stack push ch, right, and that's it, right? Now the other characters we're interested in are the closing brackets, right? So let's add in an if statement for that. All right, so now if we encounter a closing bracket, then we want to check what bracket is at the top of the stack, right? But remember that if our stack is empty, then we can't check what's on top of the stack, right? Because the stack is empty. So first, that's an edge case, right? So we want to first check if the stack is empty. Right, so the way we do that is to call stack size, right? Remember we had an operation called stack size. So if the stack is empty, which means the stack size is 0, then we know immediately that the brackets are not balanced, right? So let's just output something like brackets are not balanced, and we can immediately return, right, from our program. Okay, so if the stack is empty, we just return and say that the brackets aren't balanced. Now that we know that the stack isn't empty, we can check what's on top, right? And we may as well pop from the stack while we're at it. So let's get what's at the top of the stack. So top equals stack pop, right? So we're popping from the stack. And now we want to check if the brackets match, right? So one thing, we could do is to brute force it, which I'm going to do. So we'll just check, if they do match. So if ch is closing parenthesis and top is opening parenthesis, right? Or actually, you know what? Let's not do that. Actually, let's write a function. So what we'll do is we'll take the character that we just read in, which is a closing bracket, and then return the opposite, right? Return the corresponding opening bracket, right? So int get matching bracket. All right, and this is just going to be a series of if statements. So if ch equals closing, then return opening. Else if ch is a closing bracket, then if it's a closing square bracket, then return the opening square bracket. And otherwise, if it's a closing curly bracket, then return a opening curly bracket. Yeah, question? Yes, that's true, because we know for sure that ch is a closing bracket. So what I'll do is, if the character is anything else, I'm just going to return like a question mark. Okay, but we know that this case will never run, right? Yeah. Okay, and what I need to do is to actually put the function prototype for this at the top of the file. Okay. All right, so now let's check if the bracket that we just popped from the stack, right, does that match up with the bracket that we just read in, right? So if top equals get matching bracket ch, so well, let's check if they're not equal, right? Because if they're not equal, then we do want to just print out that the brackets don't match. Right, so actually we want to say not balanced, and then we return. And that should be it for our main loop, right? So if we read in an opening bracket, then we push it onto the stack. Otherwise, if it's a closing bracket, then we get its corresponding opening bracket and check if it matches the bracket at the top of the stack, right? And there's one remaining thing, which is what happens if we read all the inputs, but the stack isn't empty, right? If the stack still has some opening brackets in it, right? So that's one last little edge case that we have to handle. So if our stack is not 0, then the brackets don't match, right? So we just want to print out that message again and return. Right, and that's it. Maybe we can print out a message at the end here saying that the brackets do match. All right, and that's it. So now I'm going to compile the program. Whoops, let's compile. Right, so compiles. Now, the thing is, if I run this program right now, it's not going to work. Right? And the reason is the stack isn't actually implemented yet. Right? And I'm going to do that after the break. So we'll have a 5-minute break, and then we'll get back to implementing the stack. All right. Okay, welcome back. So let's continue with implementing the stack ADT. Right, so because the stack ADT only specifies what operations are provided, right, to the user, we can actually implement these operations in different ways. Okay, so one of the ways to implement a stack ADT is to use an array. Right, so what we do is we just allocate an array with a certain size, right? And if we do that, then if we insert more elements than there are spaces in the array, then we could reallocate it if we wanted. And every time we push something onto the stack, we just store that item in the first available position, right? So the first empty space, right? And then we also maintain a counter of how many items are in the stack, right? So we know where the next item goes, okay? So here's a depiction of an implementation like this. So we create a new array, right? Then when we push an item onto the stack, we push it onto so we store it into the first available index, right, which is index 0. Then when we push another item, we just store it into index 1. Then when we push another item, we store it into index 3. Now, what happens when we pop? Right? When we pop, we want to pop the most recently pushed item. Right? So we want to remove 3. So the 3 is gone, right? And it gives us 3. And when we push another item, then that gets placed after the 2. Right? So we basically fill the array sequentially. When we pop something, we remove the most recently pushed item. Okay. So that's the array implementation of a stack. Right. Another way of implementing a stack is to use a linked list. Right. So whenever we push something onto the stack, then we can simply add it to the front of the list, right? And then when we pop from the stack, we also remove from the front of the list, right? And if we do it this way, then pop and push will both be 01, right? Because it doesn't matter how many items you've pushed onto the stack, right? You're simply adding and removing from the start, right? Okay, so here's a depiction of that. So we create a new stack, which is going to be a linked list that points to null, right? It's going to be an empty linked list. When we push a 1, we insert it at the front of the list. When we push 2, we insert that at the front of the list. When we push 3, we insert that at the front of the list. When we pop, we remove 3 from the list, right? We remove the item that's at the front. Then when we push another item, we insert at the beginning of the list. So what I'll do is I'll implement this linked list version. So let's go to stack.c. Right, so I already have the struct definitions here. Yeah. Yeah, so for the array implementation, it would also be 01. Yeah, because if you keep track of the size, then you know where the last item is and where to insert the next item. Yeah. Okay, so yeah, here are the data structures. So the stack, right, contains a pointer to the front of the list, the head of the list, and it also contains the size. Okay, so what do we need to do in the stack new function, right? The function that creates a new stack. Well, first of all, we need to allocate memory for the stack struct. So what I'll do is I'll say stack s equals malloc size of struct stack. Okay, then because malloc can fail, we'll just add an error check for that. So this is just a standard check for malloc. Okay, and then we have to initialize the fields of the stack, right? So we have to initialize the head to null, and we also have to initialize the size to 0, right? Then we return the stack. So that's what we do in stack new. Well, we just create that struct, then initialize it and return it. Right, so stack free, well, with stack free, we got to return, or we got to free the linked list, right? Because we might have pushed some items onto the stack, which means we would have created a bunch of linked list nodes. So what do we have to do? Well, we have to free all the nodes, then we have to free the stack struct itself, right? But I'm just going to leave this for now in the interests of time. Right, so when we push something onto the stack, right, we create a node containing that item, then we insert that node at the front of the list. Right, so let's write the first part where we create a node. Right, so new node. So struct node star new equals malloc size of struct node. And let's not do the error check for this. And then we initialize the node. So we set the item to the item that we are pushing. And where do we point the next field to? Well, since we're inserting the new node at the beginning of the list, right, the node's next field should point to what was at the start of the list, right, originally. So new arrow next equals s arrow head. Okay, and then we make s arrow head point to our new node, right? So we've just pushed something onto our stack, and we also have to increment the size field. Yeah. Okay, what happens when we pop? Right, when we pop from the stack, we have to remove the node at the start of the stack. Okay, so let's, so when we remove a node from the front of the linked list, we gotta keep track of the rest of the list, right, before we free the node. Right, so let's say new head equals s head next. Right, and then we're now able to free s head and then set the head to the new head. All right, and remember that the user isn't allowed to use the pop operation if the stack is empty. Right, so we are allowed to leave our code like this and not perform error checks if we want. Because it's the user's responsibility to use the stack correctly, right? But just to be nice, let's just check if the size is 0. If the size is 0, then we'll print out a friendly error message like stack is empty, and then we just return some random item, return 0. Right, and at the end of the function, we should decrement the size. All right, now in the stack size function, right, because we've got the size field, we just return it. So return s size, nice and simple. And then stack peak, we can also perform a similar error check. So if the size is 0, then we print out an error message. Error stack is empty, and return a random item. Otherwise, if the stack isn't empty, then we return whatever is at the front of the list, right, without removing the node. Okay, so anyone have any questions about this? Yeah.
We
Right, so fprintf is like printf, except it lets you specify what file to print to. And std is, so when you run your program, there are three like special files which are open by default. One is std_in, which is inputs. And then we have std_out, which is where the normal output goes. Then you've got std_err, which is where the error output goes. Yeah. Okay, so I think that's it. Now let's just check if the program compiles. Okay, so line 54, we didn't return something. So let's go down to line 54. Oh, yep, so stack pop. We do need to return the item, right, that was popped. So let's redo that. All right, so I'm going to store the item that was at the top of the stack in a temporary variable, then I'll return it at the end. Okay, so that compiles now, and I've got a simple program here to just test whether the stack works. So if we run it, and the program uses asserts, right? So if you're not familiar with what assert is, assert just checks a condition, and if the condition is false, then it just terminates the program, right? With an error message. So they're useful for testing, and since we didn't get any error messages, that means all the tests passed. Okay. All right, so now that we've implemented the stack, and we've also implemented the brackets program earlier, let's just run the program to check whether it works. So we'll first check the case where the brackets do match, right? And then Control D, and it says that the brackets match. Let's check the case where the brackets don't match. So here's one of the cases where it doesn't. Right, so it says that the brackets are not balanced. Let's check when we encounter a closing bracket, but the stack is empty. Right, so it says brackets are not balanced. And let's check for if we have a bunch of opening brackets at the end, which aren't matched with anything. Control D, and it says brackets are not balanced. Okay. So program works. All right, so that was stack ADTs. Now let's talk about queue ADTs. Right, so a queue ADT is a collection of items, a linear collection, such that the first item to enter is the first item to leave. Right, so it's called a first in, first out data structure. Right, and a queue basically operates like a queue in the real world, right? So people join the queue, people enter the queue, and the first person to enter the queue is the first person to leave the queue, right? So a lot of these examples are basically just queues in real life, right? So you've got waiting lists, call centers. So whenever you call, you get added to a queue, and once it's your turn, then you get to talk with someone. Right? All right, so here are the operations of a queue. Right, so first, we've got the two main operations, which is to enter and leave the queue. Right, so these operations are called enqueue and dequeue. Right, then we've got the same operations as in this stack, so size, get the number of items in the queue, and peak, get the frontmost item of the queue without removing it. Okay, so, and we've also got the operations to create and free a queue. All right, so here are the function prototypes for the queue operations. Right, so queue new, create a queue free, free a queue in queue, add an item to the end of a queue dequeue, remove an item from the front of a queue, right? Queue size, get the number of items in a queue, and queue peak, get the item at the front of the queue without removing it. Right? And notice that we have the same constraints as with the stack. Right? When we dequeue an item or get the item at the front of the queue, we assume that the queue isn't empty. Right? Because it doesn't make sense to get an item from the queue if the queue is empty. All right, so since with a queue, we add items to the back of the queue and we remove items from the front of the queue, right? We need to add and remove items from opposite ends, right? And this could be a bit more challenging than a stack where we add and remove from the same ends, right? So can we do this efficiently? Well, let's talk about the linked list implementation, right? So if we only have a pointer to the start of the list, then we can't do it efficiently, right? Because if, let's say you add to the start of the list, right, then in order to remove from the end of the queue, you'd have to traverse all the way to the end of the list, right? So that wouldn't be efficient, right? You'd have to traverse the entire list, which would be ON. Right, but if you have a pointer to both the head and the tail of the list, so you have a pointer to the first node and the last node, then you don't have to traverse as long as you choose the right operation to perform at the start and at the end. Right? So you have to choose wisely here. So what happens if we try to insert at the front of the list, at the head of the list, and remove from the tail? Right? So if we do that, then we can certainly add to the front of the list very efficiently, right? But if we try to remove from the tail, right, then how do we, if we want to remove from the tail, right, we can do that because we've got a pointer to the tail, but how do we update the tail pointer so that it points to the new tail, right, which is the node before the last node, right? You can't do that efficiently. So instead, what we do is we add to the end and remove from the front. All right. So here is a diagram of how this would work. So this is the head pointer and this is the tail pointer. Right. So when we in Q1, we add it to the linked list. Right. And since the linked list was empty, now both head and tail will be pointing to the node. Right. Then, when we in Q2, right, we insert it at the end of the list and we update the tail. When we insert 3, we insert it at the end of the list and again we update the tail. Okay. Now when we dequeue from the front of the list. Right. So we remove the 1. Right, from the front of the list. Then when we in queue, we add to the end of the list again. Right, so we're dequeuing things in the same order as we in queue them. Right, so that's the linked list implementation, and I've got an example of that here. Queue.c. Right, so here is already implemented. Right, so the queue struct has a head and a tail and a size, and the node struct contains, it's a typical linked list node, right? So it just contains an item and an X pointer. Right, and I will put this up after the lecture so you can have a look at it yourself. All right, so here's a way of implementing a queue using an array. All right, so what we do is, again, like with the stack, we allocate an array of some predefined size. Then we're going to keep track of the indexes of the front and back of the queue. Right? And this is for efficiency. So let's say we enqueue a bunch of items. So in Q1, we store that at index 0. We in Q2, we store that at index 1. We in Q3, we store that at index 2. Right, now, when we dequeue, right, one way of doing it is to remove the 1 and then shuffle all the items down. Right? So we shuffle down to 2, we shuffle down to 3, but that wouldn't be very efficient. Right? So another way of doing it is when we dequeue, we simply we simply dequeue the 1, and now we update the index for where the front of the queue is. Right? So here, the front of the queue was at index 0, and the back of the queue was at index 2. When we dequeue, we simply update the index of where the front of the queue is. Right? So the front of the queue is now index 1, and the back of the queue is still at index 2. Okay? And that's more efficient than shuffling everything down. Yeah? Sorry? Yeah, so if you implement it this way, you could get to a situation where you have some spaces at the front of the array which are empty, but the back of the array is filled. So what you would do is you would wrap around and insert at the front. Yeah, so this is what we call a circular queue. The array is basically being treated like a ring, and we just insert around and around as long as there's space available. Okay, so that's the implementation of the queue ADT. Right, now what I want to get to is talking about a different ADT called a set. Right, so, and this will hopefully tie in nicely to what we'll cover next, which is binary search trees. Right, so what is a set? So a set is an unordered collection of distinct elements. Okay, and here we're just concerned with sets of integers. Right, so what are the basic set operations? Well, we can create a set, we can insert an item into a set, we can delete an item from a set, and we can check if an item is in the set. Right? So those are the basic set operations. So we're not going to be concerned with the more advanced operations like union, intersection, and so on. We're just concerned with these. Okay. Okay. So here's the interface to the set. So we've got one function prototype for each of the operations. So creating a set, freeing the set, inserting an item, deleting an item, checking if an item is in the set, checking the size, and displaying the set. All right, so here's what the interface would look like, right? The set.h file. Right, so we would have these preprocessor instructions. So if you look at some of the .h files later in the course, you'll see this a lot. So what this actually does is it prevents the .h file from being hash included multiple times within the program, right? Because if you include the file multiple times, then you're redefining things, right? So you're defining things multiple times, which you don't want. So this is saying if this string set underscore h is not defined, then define it. So later on, when another file hash includes set.h, it doesn't get this stuff doesn't get processed again. Right, so there's that. Then we've got the typical type def for an ADT, and then we have all the function prototypes that I showed you here. Okay. So here's one possible usage of a set. Right, so here we're reading in values, and then we're counting how many distinct values there are. Right, so a set is useful for that because when you insert an item into a set that's already in the set, then it just doesn't get inserted. Right? So we create a set, Then we scan in values, right? And for each value, we just insert it into the set. Right? And after we've read in all the values, we simply print how many distinct values there are by getting the size of the set. Right? And then we might also be interested in showing all the distinct values. Okay? Okay. So that's the interface of the set. Right, so how do we implement a set? Well, I'm going to show you 3 ways of implementing a set. So the first way is an unordered array. Okay, so in this implementation, we store all the items into an array, and the items aren't in any particular order. Right, so we have elms here, which is a pointer to an array. We have a size field, which keeps track of how many actual items there are. And then we have a capacity, which keeps track of how many items we can actually store in total. Right? How many items we're allowed to store. Okay, so how would this implementation perform? Right, well, here I'm going to focus on the 3 main operations. So we check if an item is in set, so set contains. We'll also analyze insert and delete. Right, so those 3 operations, so contains, insert, delete. Right, so to check if an item is in the set, then the array isn't ordered, right? So we have to perform just a linear search, right? So here we just loop through the array and check if they're equal to the given element. If one of them is, then we return true. Right? Otherwise, we return false. All right, so this one is, it's easy to see that it's ON, right? Because we just scan through the entire array. Okay, now how do we insert an element? Right, well, first of all, we want to make sure that we don't insert the same element multiple times, right? So we should check if the set contains the given element, right? If it does contain the given element, then we return, right? Because we don't want to insert again. Then we make sure that we haven't run out of space in our array. And then we insert the element after the last element. Right? So the way we do that is we insert the element at index size. Right? That's because, for example, if there are 5 elements, then the elements are stored at indexes 0 to 4. So index 5 is where the next element would go. Okay? Then we increment size. All right, so the time complexity of this one is also O of n, right? Because set contains, we already saw earlier, is O of n, and inserting after the last element is O of 1, right? Because you can easily calculate where that element goes. All right, now how do you delete an element? Well, you loop through the array to find the element. And once you've found the element, we can do a nice trick. Because the element is unordered, we can simply replace the element with the last element in the array. Right? So that's what we're doing on this line here. Right? So if the element exists, override it with the last element, then decrement size, then return. Okay, so the time complexity of this is also ON. All right, so that's the unordered array implementation. So all 3 of the operations that we're concerned with are ON. Right? Now here is another implementation. Right? So a sorted array. So in this case, our array is sorted. So you might have an idea that we can use binary search, and you'd be correct. Right? So in order to check if an element exists, we can perform binary search now, right? Because the array is sorted. So here's the implementation of binary search that you would have seen earlier. Right, so the complexity of this would be O of log n. right? Because it's binary search, and we know binary search is log n. Now, how do we insert an element? Well, inserting we can also do with binary search, right? So the thing with binary search is, as well as using it to find an element, we can also, in this case, we can use it to find the index of the smallest element, which is greater than or equal to the element we're trying to insert. So let me give you an example. So if we're trying to insert the value 6, right, then we use binary search to find the smallest element, which is greater than or equal to 6. Right? In this case, it is 7. Right? Now, if 6 is in the array, then the element that we would get is 6, right? Because, yeah, we're trying to find the smallest element, which is greater than or equal to the element we're trying to insert. Okay, so use binary search to find that, which I already mentioned. Then if the element is the given element, then it already exists, right? So we don't need to do anything. Otherwise, we insert the element at that index, and then we shift everything greater than it up the array. All right, so going back to this example again, if we wanted to insert 6, then we would insert 6 over here, and we would shift the 7 and 9 up the array, okay? All right, so what is the time complexity of that? Well, binary search, it lets us find the insertion points, right, where we want to insert in log n time, because binary search is log n. But the downside is because we have to make sure the array remains sorted, we have to potentially shift n elements, right, which is on. So, despite getting the benefit of binary search, the shifting still makes it on. Yeah. Unfortunately, we can't do that because it's an array. If it's a linked list, it's very easy to insert because you can just rearrange the pointers. But an array, unfortunately, doesn't work that way. Yeah. 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 So if we cut out part of the array, then re-added them, so re-copy the elements back, it would be on as well. Yeah. Okay. So how do we delete an element? Right. Well, we can once again use binary search to find the element, right? And if the element exists, then we just shift everything greater than it down, right? So going back to this diagram, let's say we want to delete 4, right? We use binary search to find it, which would be log n. Then we shift the 5 and 7 and 9 down. Okay, so what is the time complexity of that? Well, once again, binary search lets us find the element in log n time, but we have to shift up to n elements down the array, right? Which would be O of n. Okay, so here is, so just to summarize this, so we can use binary search, which is great because it's log n, but because we have to maintain the order of the array, that requires shifting, right, which causes insert and delete to be on, unfortunately. Right, so here's the third implementation I wanted to talk about, which is an ordered linked list. Right, now, you might be thinking, well, a linked list, that's going to be a garbage implementation because you know that with linked lists you have to traverse from the start. Right? So to find anything, you have to traverse from the beginning of the list. So finding anything would be O of n, right? And you'd be mostly right. So to check if an element exists, then we just traverse the linked list until we find the element, right? Which is O of n. Right now, so yeah, we have to traverse from the start no matter what we do. So insertion and deletion would also be on, right? But this sort of hides one major advantage of linked lists, which is that finding the point to insert or delete is on, because you have to traverse the list. But once you've found the insertion points, you can actually insert and delete a node very efficiently. Right? So if you know where exactly to insert or delete the node, all you need to do is rearrange a couple of pointers, and you can insert or delete the node in O1 time, right? Because you don't have to do any shifting with linked lists. All right, so just to summarize, well, if we have an unordered array, right, then checking if an element exists, inserting and deleting are all on. Now for a sorted array, we can easily use binary search to check if an element exists, which is log n, but inserting and deleting are on, right, because you have to perform shifting. Now, if we have an ordered linked list, right, all of these operations will be on because we have to traverse the list. But just remember that with linked lists, you don't have to do any shifting, right? So if you can somehow find where to insert more efficiently, then perhaps we can, implement the set ADT more efficiently, right? And what that leads to is our first data structure, which is going to be a binary search tree. So I'll do a quick introduction to binary search trees, but then we'll get into the meat of it on Wednesday. So let me just start talking about trees, then we'll continue. So these aren't on the website yet. These slides aren't on the website yet because I didn't anticipate that we would get to this. But just to introduce things, what is a tree, right? So we're not talking about an oak tree here, but we're talking about a data structure consisting of nodes, right? Where compared to a linked list, where each node has exactly one next node, right? So it's a linear data structure. A tree is a branch data structure, right? Where every node may have multiple children, right? Multiple successors. Right? So each node may have multiple other nodes as children, and each node is connected to one parent except for the root node. Right? So you have one node, which is the root node, and then all the nodes sort of, are descendants of the root node. Okay, and because of that, trees do not contain cycles. Okay. So here are just some examples of trees in the real world. Right, so first of all, your file system, like the file system on your computer, is a tree, right? Because you've got a single root directory, and then you've got subdirectories of that, and each of those directories will have subdirectories and so on. Another example of a tree is an organizational structure, right? So a company has a bunch of departments, might have a research and development department, sales department, the manufacturing department, and so on. And each of those departments have smaller divisions, right? So sales could be domestic or international, and so on. Right. Another example, which isn't quite physical, but it's more abstract, is a decision tree. Right. So each node of the tree is basically a question, binary question, yes or no, and the leaves are, the outcomes, right, at the end. All right, now here's something that you might not have thought of as a tree, but you can use a tree to decode Morse code, right? So You might know what Morse code is. So Morse code, is an encoding of letters using dots and dashes. Right. So what you can do is, every time you see a dot. So when you're decoding Morse code, every time you see a dot, you go left. Every time you see a dash, you go right. Okay. So if you see dot dash dash, then you go from the start. You go left, right, right, and that gives you the letter W. Okay. All right. Now, so these are some examples of trees in general, right? But now let's narrow it down a little bit to binary trees. Right now, binary trees are trees where each node has up to 2 child nodes, right? That's it. So above, there were some examples of binary trees. So this was a binary tree. This was also a binary tree. Now, these are not binary trees, right? Because each node can have more than 2 children. Right? And these child nodes are typically called the left child and right child. All right. Now, so that's a binary tree. Now, what is a binary search tree? Well, binary search tree is an ordered binary tree. Right? Now, what does that mean? So what it means is for each node, all the values in the left subtree are less than the value in the node, and all the values in the right subtree are greater than the value in the node. Right, so for example, we have 3 binary search trees here. Now, this tree here with only 1 node is obviously a binary search tree, right? Because it's just a single node. It doesn't have any subtrees. So this condition here is true by default, essentially. Right. This tree in the middle consists of 3 nodes, and we can see that these conditions are true. Right. So for this node here, 5, all the values in the left subtree, so which is only this value here, are less than the value in the node, and all the values in the right subtree are greater than the value in the node. Okay, and for this tree, the properties are also true. Right? So just keep in mind that these properties hold for every value in the tree. Right? So it holds for 5, but it also holds for 2, for example, and it also holds for 7. Right? So if we replaced the 3 with a 6, for example, then like the property wouldn't be true anymore. Like it wouldn't be a binary search tree, right? Because if, like for this node 5, we would have a 6 in the left subtree of 5, which violates this first condition here. All right. Now, with binary search trees, we can define them recursively, right? Just like with linked lists. So think about how linked list is defined, right? A linked list is either empty or it has a node followed by a smaller linked list, right? That's how we can define a linked list recursively, right? And that's one of the reasons why we can use recursion on linked lists, right? With binary search trees, a binary search tree is either empty or it consists of a node with 2 subtrees, right? And because of that, we can also use recursion on binary search trees. And they're very useful for binary search trees, especially because with linked lists, you can easily implement things using a loop, right? Because you just loop through the nodes in order. With binary search trees are a branching data structure, right? So if you use a while loop, right, you have to go either left or right. So which way do you go? Well, if you go left, then you're going to miss everything on the right subtree, but if you go right, you're going to miss everything in the left subtree, right? So recursion lets us, traverse both subtrees in order to do whatever we need to do, right? Okay. So let's talk about why we use binary search trees, and then we can wrap up. Right, so why do we use binary search trees? Well, searching is an extremely common operation, right? In computing, in other areas as well. For example, selecting records in a database or searching for pages on the web. Right? And typically, there's a very large amount of data. Right? There are millions, tens of millions of web pages. So searching with the linked list isn't going to cut it. Right? So we want a data structure that allows us to search very efficiently. Right? And what are some methods so far that we've explored for searching? Right? So just before, when we were looking at the set ADT, we looked at an ordered array. Right? We also looked at an unordered array, but that wasn't very good. So let's talk about an ordered array. Right? So with an ordered array, finding, when we're searching and inserting stuff, right, finding the insertion point or searching is O log n due to binary search. Right? So we can find where to insert or search very easily, very efficiently. But inserting is ON, right, because we need to shift items up or down to preserve the order of the array. Okay, so the disadvantage of an ordered array is the need to shift items, right, which is ON. If we use an ordered linked list, then finding the insertion point or searching is ON because of the nature of linked lists. Right? You have to start from the beginning and loop through each node, right, until you find the item. Right? But if we found the insertion point, then inserting is O1, right? Because we don't need to shift anything. Right? We just need to rearrange a couple of pointers to insert. So what binary search trees do is they give us the best of both of these. So they give us the best of both worlds. Right? Now, searching in a binary search tree is similar to how binary search works. Right? And we'll explain this in the next lecture. But also, a binary search tree is a linked data structure, right? Similar to a linked list. So there's no need to do any shifting. So once we've found where to insert, right, we can insert very efficiently. Right? So this gives us the best part of both of these implementations. Right? So binary search trees, it gives us the efficiency of a binary search. And it also gives us the efficiency of not needing to shift. Right? And in the next lecture, we'll talk much more about binary search trees. Question?
So it increases efficiency of both the array and the linked list.
Well, it's not an array or a linked list, but it gives us the advantage of both of them. Yeah, and we'll talk about that on Wednesday. So I'll see you guys on Wednesday.